This presentation deeps into work titled ImageNet Classification with Deep Convolutional Neural Networks. The research was conducted by Alex Krzyzewski, Ilya Sutskever, and Jeffrey E. Hinton. This seminal paper introduced an architecture that redefined visual recognition, achieving a dramatic and record-setting breakthrough in ImageNet performance. Object recognition in realistic settings requires models trained on immensely large datasets to handle high variability. The emergence of ImageNet, with millions of labeled images, necessitated the development of extraordinarily large capacity models, specifically deep convolutional neural networks. This presentation will provide a comprehensive examination of a seminal 8-layer CNN architecture that achieved a breakthrough in visual recognition accuracy. We will detail the unique structural components, including the 2-GPU parallelization strategy and the adoption of non-saturating rectified linear units. Furthermore, the discussion will cover regularization techniques essential for training this 60 million parameter network. Finally, we will review the compelling record-setting performance achieved during the ImageNet large-scale visual recognition challenges. We begin by establishing the properties of the foundational ImageNet dataset. Current object recognition efforts rely fundamentally on machine learning methods. Historically, performance was limited because available image datasets were relatively small, often containing only tens of thousands of images. However, recognizing objects in realistic settings demands models trained on much larger datasets to account for considerable variability. ImageNet emerged to meet this demand, providing over 15 million labeled, high-resolution images spanning thousands of categories. To learn about thousands of objects from such immense data, a model must possess an extraordinarily large learning capacity. Deep Convolutional Neural Networks, or CNNs, constitute a class of models uniquely suited for this complex task. Their ability to scale in depth and breadth, combined with strong assumptions about image structure, makes them ideal for processing the ImageNet dataset. Following the introduction to deep convolutional neural networks, the foundation of this work relies on the ImageNet dataset. The ImageNet Large-Scale Visual Recognition Challenge, or ILSVRC, provides the crucial dataset used for training and evaluating the model. This subset of the larger ImageNet collection encompasses 1.2 million training images distributed across 1,000 distinct object categories. The full challenge dataset also includes 50,000 images for validation and 150,000 images reserved for testing the final performance. Since the network architecture demands a fixed input dimension, all variable resolution images were uniformly scaled to 256 multiplied by 256 pixels. Critical to the challenge are the performance metrics, the top 1 and top 5 error rates, which quantify the classification accuracy of the network. This comprehensive dataset setup enables a rigorous assessment of the proposed deep learning architecture. The detailed figure outlines the architecture of the large convolutional neural network, featuring 8 learned layers in total. This sophisticated structure comprises 5 convolutional layers, followed by 3 subsequent, fully connected layers. To manage the immense computational load associated with the ImageNet dataset, the network's processing is explicitly divided across 2 graphics processing units. One graphics processing unit handles the upper path of the network layers, while the second handles the lower path, communicating only during specific intermediate stages. The network begins with a 224 multiplied by 224 multiplied by 3-dimensional input image. This input progresses through several high-capacity transformation stages before resolving into a final Wasserway output layer for classification. This novel division of computational responsibility is a core element for enhancing training speed, which will be discussed further. Traditional saturating activation functions, such as the hyperbolic tangent, significantly impede the speed of training deep convolutional neural networks via gradient descent. To overcome this limitation, the authors adopted rectified linear units, or ReLUs, which are characterized by their non-saturating nonlinearity. The visual evidence directly compares the training error rates of a 4-layer network utilizing real loose, represented by the solid line, against an equivalent network employing tan units, shown by the dashed line. It is evident that the ReLU network reaches a 25% training error threshold approximately 6 times faster than its saturating counterpart. This acceleration demonstrates that the employment of ReLUs was fundamental to making the experimentation with large-scale deep learning models viable. Previous slides highlighted the substantial size of the 8-layer convolutional neural network. However, the memory limitations of a single graphical processing unit necessitate a parallel training strategy. Consequently, the substantial network architecture was spread across 2 graphical processing units utilizing direct cross-device memory access. The scheme partitions the workload, essentially placing half of the network's kernels or neurons onto each individual graphical processing unit. A crucial aspect of this parallelization involves restricting communication between the devices to only occur in specific layers. For instance, while kernels in Layer 3 receive input from both devices, Layer 4 kernels are restricted to inputs originating only from the same device. This method allows researchers to precisely tune the amount of cross-device communication relative to computation. Ultimately, this specialized 2 graphical processing unit architecture effectively reduces the top 1 error rate by 1.7%. Compared to comparable smaller single-device training. The network utilizes local response normalization, a specific form of brightness normalization rather than contrast normalization. This normalization scheme is inspired by lateral inhibition observed in real neurons, which promotes competition among different kernel outputs. The calculation sums responses over n adjacent kernel maps at the identical spatial location. Importantly, this process is applied following the rectified linear unit nonlinearity in select convolutional layers. The required hyperparameters such as k, n, alpha, and beta are carefully tuned using a separate validation dataset. Implementing local response normalization significantly enhances performance, reducing the overall top 1 error by 1.4%. The previously described deep convolutional network architecture contains a substantial 60 million trainable parameters. Despite the size of the ImageNet dataset, this massive parameter count makes the network highly susceptible to overfitting. The constraints provided by the 1,000 classes of the ImageNet Large-Scale Visual Recognition Challenge were found to be insufficient for robust generalization. Consequently, the team employed specific regularization techniques to improve performance and feature learning. 2 primary strategies were utilized to combat this challenge and ensure the model learns robust features. These strategies include deploying extensive data augmentation and utilizing the regularization technique known as dropout. The 8-layer convolutional neural network performance on the ImageNet Large-Scale Visual Recognition Challenge 2010 test set is summarized in the table. The deep network achieved compelling results with a top 1 error rate of 37.5%. Crucially, the top 5 error rate was reduced to 17.0%, establishing a new benchmark for image classification accuracy. These outcomes represent a significant improvement over the previous state-of-the-art methods, which are listed in italics. For comparison, the sparse coding method previously achieved a top 1 error rate of 47.1% and a top 5 error rate of 28.2%. This substantial reduction in error validates the effectiveness of the architectural decisions, including the use of rectified linear units and dropout techniques discussed previously. Attention now shifts to the 2012 competition results, which provided an even stronger validation of this methodology. Presenting the official error rates for the ImageNet Large-Scale Visual Recognition Challenge 2012, this table confirms the breakthrough performance of the Deep Convolutional Neural Network. The established baseline, represented by the SIFT and Fisher vectors approach, yielded a top 5 test error rate of 26.2%. In stark comparison, a single uncombined convolutional neural network model achieves an 18.2% top 5 validation error. Crucially, the ensemble approach of averaging predictions from multiple models drastically lowers the error rate, seen by the 5 convolutional neural networks achieving 16.4%. Models denoted by an asterisk indicate pre-training on a larger ImageNet dataset, further improving the overall results. The ultimate winning configuration, utilizing an ensemble of 7 pre-trained convolutional neural networks, reached a top 5 test error rate of 15.3%, demonstrating an unprecedented advancement in visual recognition accuracy. The visualization displays the 96 convolutional kernels of size 11 multiplied by 11 multiplied by 3 learned by the first layer of the network. These kernels reveal that the network has successfully learned a variety of frequency and orientation selective features, alongside several colored blob detectors. Crucially, a distinct specialization is evident between the kernels processed by the 2 separate graphics processing units, a direct consequence of the restricted connectivity scheme introduced previously. The top 48 kernels learned by Graphics Processing Unit 1 appear primarily color agnostic, focused on extracting basic edge and texture information. Conversely, the bottom 48 kernels learned by Graphics Processing Unit 2 are predominantly color-specific, specializing in detecting chromatic patterns. This consistent division of labor confirms that the parallel architecture facilitates the emergence of specialized feature detectors independent of initial random weight assignments. Qualitative evaluation extends beyond simple error measurement to probe the model's learned representations. Figure 4 demonstrates 2 primary methods for this analysis. The left panel shows the network's top 5 probability predictions for various test images, revealing that plausible alternatives are frequently ranked highly, such as grouping a specific leopard with other felines. The right panel assesses semantic similarity by examining the feature activations induced in the last 4096-dimensional hidden layer. Images that produce activation vectors with a small Euclidean distance are considered similar by the network. This analysis confirms that the learned features capture robust high-level attributes. For instance, the retrieved training images exhibit objects in various poses, confirming semantic rather than pixel-level similarity. This concluding section summarizes the primary findings and outlines the path for future research. The study confirms that a large and deep convolutional neural network is capable of achieving record-breaking results on a highly challenging dataset using purely supervised learning. The depth of the architecture is critical. Removing a single convolutional layer, for instance, results in a loss of approximately 2% in top 1 performance. Although not utilized here, the authors expect that unsupervised pre-training will yield further benefits, especially when the network size is significantly increased. Immediate future work involves continued scaling of network size and training duration. Ultimately, the goal is to apply these very large and deep networks to video sequences, allowing the models to capitalize on the helpful temporal structure inherent in video data.